Okay, I will talk about the test here just briefly, and then we'll get back to talking about optics. So we'll talk about lenses and thin lens equations. If you look at the tutorials, that's not how you spell tutorial, the tutorials that I have on YouTube, I go through how to do the ray construction very carefully for a number of different scenarios. You're going to have to do one of those scenarios on the next test. So if you have any confusion, go look at those after today's lecture. That's just going over a homework problem that we did before class. Here is a test problem that is a very good test question, but is one that every single student missed. So a proton is traveling at a speed of 256 meters per second east in a region where the magnetic field has a strength of 0.360 G Gauss and a direction that is 26 degrees down from north. What is the magnitude of the magnetic force on the proton? And I said, everyone in the class got this wrong. Do you remember doing this problem in class? This is one of the example problems that you guys did, and then I explained afterward. The numbers are changed, but the problem is the same. What did everybody do wrong? What do you think? The angle. The angle needs to be 90 degrees because what's the angle between east? Okay, east would be, I gotta get my directions right. That's north, that's west. So east and 26 degrees south of, or not down, excuse me, of north, that's 9 degrees. And so your angle is 90 degrees. I know it had an angle in there that wasn't 90 degrees, but the angle that you're looking for is the angle between the two vectors. And there was one person who simply wrote, I try to find the equation with the variables for their method of solving. Well, there has to be thought involved as well, because it's more than just I put numbers in an equation and crank out a number. That's not physics. In fact, part of the reason I put this question on the test and the next question is because we had Dr. Roddy on campus on Monday, and we were noticing that last year the MCAT scores were much lower than normal. And why? Primarily, people aren't thinking through the problems. They're not applying the critical reasoning skills. And the whole reason for physics is for you to learn those critical reasoning skills, to not just, let's put numbers into an equation and get an answer. And so I wanted to make sure that I'm emphasizing the critical reasoning skills because I want you guys to have good MCAT scores. That is one of my clear goals for this class, those who are pre-med. Okay, so the problem there, identifying what the angle is. The next one that had a big problem, now this one not everybody missed. There are a few that got it right, but most people missed this one as well. You have two long wires cross each other at a closest distance of 1 millimeter. The first wire carries this current north, while the other wire carries this current east. That's right. A lot of people just use this equation but this equation does not apply. When does that equation apply? Only when the wires are parallel. If they're not parallel, then you have to do just like we did in this problem in class. You say, okay, magnetic field created by the top wire underneath, using the right-hand rule, it's going like that. And then for each piece of the wire, force is equal to IL cross B. And so you look at that and you say, okay, if I have the wires that are perpendicular, so if I have a wire that's perpendicular, so a wire that's going like this, this wire here is perpendicular to the upper wire, then the angle between them is 0. That is between the magnetic field and the current, and thus the force is 0. So once again, this is one where you have to not just look for an equation that has the right variables, because I mean, this equation had the right variables, but I should have had newtons per meter here. But since the correct answer was none of those, the one with no units is still correct. How to get what? Did I add them wrong? Well, did my spreadsheet add them wrong? Oh, I wrote something wrong. It's okay. Did I write the same on the second page?
Yeah.
Oh, I put this number instead of that number.
Yeah.
Okay. Anyway, I want to go over these because these were the reason I graded out of 20 or out of 80 instead of out of 100. Because I don't want people to feel penalized because they weren't thinking, even though thinking is an important part of physics. I want to emphasize the importance of thinking about the problems and not just looking for an equation and putting numbers in. Any questions about the exam? All right then. Getting back to optics. We had the mirror equation, which we will learn in a few minutes is also called the thin lens equation. It works for both a mirror and a thin lens. So this equation here is the one that's the mirror equation. And you had homework that you had to use that on. One thing that a student asked me about, just to make sure we're clear, if you have the problem that you're doing that's specific to this, you're finding what distance image is. If I want to solve this for distance image, there's only really two steps. First, you subtract distance 1 over distance object from both sides. And then what's the second step?
Isn't it inverse though?
You have to take the inverse of each one. Now notice the inverse is of the entire side, not of the terms. So what that gives you is which is not the same as F minus D object. That would be a different number. You can just put in numbers to convince yourself. Let's say that F is 5 and D object is 10. 1 over 5 minus 1 over 10 is 2 over 10 minus 1 over 10, 1 over 10. Your answer would be 10. But if I did F minus D0, I would have had 5 minus 10 is minus 5. Very different answers. So make sure that you do your math straight on that. Yes, Diana.
It doesn't give us the option to put so we have to
Right.
just put R over 2. So like
Yes.
So in that case, instead of R over 2, would we use 2 over R for 1 over F?
Well, remember, you have F is R over 2.
Right.
So if I put F is R over 2, then that's going to be replace the F with R over 2, or invert and multiply 2 over R.
So it would be 2 over R.
And undo those last two things just so it doesn't look all, or last 7 things. There we go. Just so it doesn't look scruffy. Right, I was answering generic rather than specific to that problem. That's why I didn't substitute it in. Okay, so we had this problem and we did the work on it. Right? Today I want to make sure we do the ray tracing right. So with the ray tracing, we're using the definition of focal length to our advantage. So what was the definition of the focal length? Or the focal point? Let's start with that, the focal point.
Radius of 2 over 8.
That was how we calculate for a spherical lens, or mirror, excuse me. But what was the actual definition when I did it on the board with the light?
That's the point where the light focuses.
the point where parallel incident rays focus. So it doesn't matter what direction the light is coming in, it's going to go through, or not direction. It doesn't matter what the height is if it's coming in parallel. So if the light ray is coming in, let's say, keep forgetting that is not a ray. Once again, let's undo that. And we'll just use purple. And that's not a line. I have red, green, and black preset, so red it will be. So that is to the best of my artistic ability, a parallel ray coming into the mirror. Parallel to what? To the principal axis, to this black line. So this black line is the principal axis. It's parallel to that. The focal point was the point where any ray that comes in parallel to that principal axis is going to go through. So it's going to reflect like that. So it went through the focal point. And you'll notice my artistry is not perfect, especially on this. And so we have a name for this. We call this the parallel ray, or P ray. So the P ray start at tip of object, go parallel to principal axis, reflect through focal point. So that's the first ray. Now, light works the same way forward and backward. That's an important thing to know about light. It works the same forward and backward. So that means that if I do the reverse of that, if I go from the tip of the object through the focal point, that's the reverse. Goes focal point to the mirror. How's that going to reflect out? It's going to reflect out parallel because it's reverse. Light works the same forward and backward. If you think about this in reverse, so I'm going to put arrows on this. The arrows are going like this, but if you reverse the direction, you'd be coming in parallel and then reflecting back through the focal point. So we call that the focal ray. Or F ray for short. Start at tip of the object in. Tip of object. Go through F and reflect parallel. Parallel to what? The principal axis. Now, two rays, where they meet, that must be where the image is, because the image is where the rays meet. So we can see where the image is, but we always do a third one to check. So on the test, you will have to do 3 rays. There are 2 rays that you can choose from for a mirror to get your third one. You can choose what's called the center ray, and you can choose what is called the vertex ray. I'm going to illustrate here the vertex ray first. Green. Vertex ray. This point right here is called the vertex. The place where the principal axis meets your mirror or lens. The vertex ray goes from the tip of the object to the vertex. And at the vertex, your angle of incidence is this angle right here. So the angle of reflection needs to be the same. So it's going to reflect back to the same position down below. That is, it's symmetric. And so it's going to go like this. And you can see my artistry is bad because those don't come close to crossing each other at the same location. I'm going to have a crossing here. Oh, change pens. A crossing here, and some crossing that's way out there.
You say with the vertex It's the place where the principal axis and the lens.
And the mirror, or lens when we get to lens. So the principal axis is normal to the surface of the mirror, and when you hit the vertex, that means your angle of incidence is the angle between the principal axis and the. What was that? The principal axis is normal to the mirror. Normal to the surface of the mirror going through the center.
And then that line that you drew from like the vertex to the thing in green, what is that showing?
So this here, this is supposed to be this angle and this angle being the same. Yeah. That's always true, but for the vertex ray, it's one that we can map out. For the other ones, we're using that to get our parallel ray and our focal ray, but we're not using it directly, we're using it indirectly. So how do we what? How do you draw this perfectly? The way to draw these, quote, perfectly is using something where you can measure distances. So the reason I have this there is because I was trying to get the distances horizontally correct so that each one of those ticks is 5 centimeters. But I didn't do anything for measuring the verticals, and I didn't do anything to make sure my lines were parallel. So if I'm going to do this like on the test, I measure the height of my object, and then I go over here and I make a mark that's the same height. So like the height of my object here is going from 3 to 4 and 15/16. So from 3 to 4 and 15/16. If that was truly parallel, it should have hit there. And that would have made a big difference, right? So you use your measuring device to make sure you have truly parallel incident ray, and you make sure, just like before, if I would have placed the second one right, the second one would have passed through right there, so it would have been higher there for the. So that's how you do them correctly. And I just, doing it on the tablet, it's hard to get those things correct. And on the test, I will accept a certain amount of error because we're humans. No one's going to have it exactly right. The only way to get it exactly right is if you first figure out exactly where the image is supposed to be and make your lines so they match that. But what I'm going to be looking for when I'm grading this is if you describe the 3 rays correctly that you use. So vertex ray goes from tip of object to vertex and reflects symmetrically below the principal axis. I'm going to be looking to see if you described each of the rays correctly, and then if you actually drew them correctly. So if they don't exactly match where they're supposed to meet, that's not what I'm measuring. Now, if they're way away from where they're supposed to meet, you probably didn't draw them correctly. So you have to, you're going to have to practice some of these. Make sure that you can construct them.
So all the lines that you drew, you have to be able to draw.
Yes. And there's one more you could choose from, but only in the case of a mirror. So for a mirror, you also have the center ray. The center ray starts at center and goes through tip of object or reverse. That is, depending on the position, reverse. On the situation, it might start at the tip of the object and go through the center and then reflects straight back on itself. So in this problem, what was the radius of curvature for the mirror? Probably don't remember at this point, right? But it was 15 centimeters. So here is the center of curvature. So that center ray is going to, I'll do this. It's going to start here and go through the tip to the mirror, and then it reflects straight back. And so that's how you do the center ray. But like I said, that can only be done with mirrors, not with lenses. So I don't emphasize that because the other three, you can do it whether it's a lens problem or a mirror problem. So 4 total rays, you have to do 3 of them on your diagram. If it's a lens, it's going to have to be the first 3 I did. If it's a mirror, you can substitute the center ray for any of the other ones.
The center ray being green.
The center ray is the red one. Well, the thin red one. It's the one that started at the center of curvature. Whoops.
Oh, the thin red one.
It started at the center of curvature, went through the tip of the object to the mirror, then came back. If the object was farther away than the center of curvature, then it would have started at the tip of the object, gone through the center of curvature, come straight back.
Got it.
So the key is you take a straight line from the center of curvature to the tip and extend it to wherever the image is. So any other questions about the ray construction? Eventually, sure.
Will there actually be more problems or like some example we can practice making these or something, or?
You will have homework problems with it, yes. And like I said, there's the tutorials for each of the possible variations on YouTube. Now talking about lenses. If we're going to talk about lenses, we start by talking about the index of refraction. Now, we already talked about the index of refraction once, but we are coming back to make sure we're real clear on it. The index of refraction, defined as the speed of light in vacuum, c is our symbol for speed of light in vacuum, divided by the speed of light in whatever the medium is, v. And here you can see some typical indices of refraction. Air, 1.000293. That's close enough to 1, we don't worry about it, right? Carbon dioxide, hydrogen, oxygen, all of those in the gaseous form, very similar. Liquids, you can see water here is basically 4/3. So sometimes we just use 4/3 of fraction for the water just to make it look cleaner. But these have ranges around 1.5. Solids ranging from diamond at a very high number to polystyrene that's pretty low. Like I said, acrylic is the same as that polystyrene. Yeah, ice is lower. You're right. I didn't notice the ice. So those are indices of refraction. Now, the frequency cannot change when you go from one medium to another. My simple brain way of making sure I remember that is if I have 2 strings that are dissimilar. So I have one that's a heavy string like, a thick twine, another one that's a light string like dental floss. If I'm going like this, I have a certain frequency and a certain wavelength going through the dental floss. When it hits the knot between the two, the knot is going to go up and down at the same rate that the string is. And then the wave that goes through the other side is going to be at that same frequency. If the frequency in the heavy rope is different than the frequency on the light rope, then they would actually break apart at the knot. They wouldn't be held together. So they have to both be oscillating at the same frequency the knot is. But that means the wavelength is going to change because we have a fixed relationship between wave speed, frequency, and the wavelength. And so just solving this upper equation to say that V is equal to C over N, and putting that in for V, you find that the wavelength in any medium is equal to the speed of light over the frequency in that medium times 1 over N. That's the wavelength in vacuum. And so the wavelength is equal to the wavelength in vacuum over N. That way I wrote that as poor. So wavelength is equal to the wavelength in vacuum divided by the index of refraction. So the wavelength shortens when you go into any medium other than vacuum air by that relationship. So it's important to be able to calculate that wavelength shift. We've already done Snell's law. I'm not going to go over that again. So with the thin lenses, we want to make sure that we can do the same type of work with thin lens that we did with a mirror. So we have the principal axis, the axis of a lens that passes through the centers of curvature of the lens surfaces. Now, what shapes do we have for lenses? We have all kinds of shapes. Where's my shape? Here's the shapes that are the common shapes. So the principal axis in all cases is going through the centers of curvature of both sides. So if this is a circle, well, take this. If you made this into a big circle, its center of curvature would be like here. This one here, center of curvature, would be way out to the left of that same height. And so the principal axis is going like, well, I'm a little low, but you get the picture through each one of these. I wish I was better at artistry. Once again, I went low. Yeah, I've thought about that many times. So there it went high. And you see why my ray diagram didn't come out the way I wanted it to. Trying to freehand is impossible for me. That'll do it. So that's where the principal axis is. Now, in these types of mirrors, we have two different fundamental types, diverging versus converging. Diverging means that when light goes through, it's going to spread out. So once again, let me bring out my toy set and show these. So I have some examples of diverging and converging lenses here. I have my ray box. And in a moment, I will turn off the projector and erase the screen. So here I have parallel rays, and we already saw something like this. Well, I think I used this before. Why are the rays converging inside this material?
Because it's that's polystyrene, right?
It's acrylic.
I would say acrylic.
It's acrylic or polymethyl methacryl. It's one of two.
It's because the refraction index refraction factor.
The index refraction is bigger than air, and so the light is refracting toward the normal. The normal up here is pointing down and to the right, but down here it's up and to the right. So it's bending toward that in each case. So it's converging, coming together. Now this second surface is a flat surface. If you look carefully, you see the light does bend here, even though it's a flat surface, because it's bending away from the normal because it's going into a faster medium on the backside. If I went like this, now it's coming in normal, so there's no deviation in the front. The backside's converging because, again, it's going away from the normal. The normal is up like that, so it's going away from that, bending downward. Here, the normal is down to the right, bending upward. You can clearly see that the focus ain't perfect, right? Just like with a mirror, a spherical, or in this case, circular shape is not the correct shape. If you limit yourself to just what we call the paraxial rays, the ones that are close to the center, it's much better crossing than if you take ones that are farther. Here is using a normal lens, a normal converging lens. Okay, that's pretty good focus. It's not perfect. If you look carefully, you can see there's a line just below there that doesn't quite match up. Comes to a focus. So we have an image, because that's where the rays come together, focus, that's where the image is. Here's a good question for you. What will happen to the image if I block the bottom half of the rays?
Wouldn't they just be cut out?
Yes, so what happens to the image? Is it still meeting the same place?
Oh, yes.
Yes, it is. The only thing that's different is we don't have as much light meeting there. So if you have a lens and you cut that lens in half, which I, of course, am not going to do here. If I cut this lens in half, effectively it's just cutting out these rays. So I have the same image if I cut the lens in half. It's just not as bright. A lot of people get that confused. They tend to think, oh, it's going to cut out half of the image. No, it's just cutting out half of the light, but you still have the light from every point in the object that comes together meets. So that's converging because both surfaces are making the light converge, just like we saw with this. Both this way and this way made it converge. Now, if I change to this, we call a double convex or biconvex lens. If I change to one that's concave on both sides, then what's it going to do?
Doesn't it diverge? Oh.
Diverges. Now, with this one here, we can easily identify the focal point, right? Comes to a focus right here. And so the focal length is that distance measured from the center of the lens to out here. Yes, David.
What if we put the diverging lens at the focal point? Well, I don't think anything happens.
Virtually nothing. Because at the diverging lens, at this point, we basically have two parallel faces that it's hitting. So virtually nothing. If we put it out here, see it moved it farther. If we put it here, you can, okay, gotta make sure we stay in there. But it moves it a different distance depending on how close they are together. So the closer they are, the farther away it is. Bring out, it moves closer.
All right, that's pretty cool.
And that's something we have to learn to deal with. Not today. Okay, so this, put in the same place. Now what are the rays doing? They're diverging. Does it have a focal point? Oh. We had some yeses and some nos. You're right, Max. It's a virtual because if I take this line here, this line, okay, I'm missing. And I extrapolate those back, I'll find that they meet somewhere back here. And I have that focal length. Is a positive focal length for the converging lens, yes or no?
Yes.
Yes, the converging lens has a positive focal length. Why? Because the focal point came on the side where the light went to. Does this one have a positive or negative focal length? Positive or negative? Negative. Why? Because the focal point is not where the rays are. The rays are on this side, and the focal point's on this side. So that's why it's a negative focal length. So negative focal length is diverging. Positive focal length is converging. That's true whether it's a lens or a mirror. So in this diagram, the diverging lenses all have F negative. The converging all have F positive. What's the difference in those? Well, fundamentally, the difference is these have a net convex nature. These have a net concave nature. Okay, so I see Max has eyeglasses on. So Max, are your eyeglasses converging or diverging?
Probably diverging.
Okay, now why do you say probably diverging? I want us all to be able to answer this question eventually. That's why I'm pushing you because you can actually check them.
This is going to bring the image back to my eye, so it has to like put the time.
What it's doing, we'll talk about later. Right now, just taking the physical shape.
Oh,
If you feel them, where are they narrowest or
in the
thinnest?
middle. So,
If they're thinnest in the middle,
yeah.
then they are a net concave and they're diverging. Most people's eyeglasses are diverging lenses.
Does it change if they're like bifocals or trifocals or anything?
Usually not.
What about if nearsighted or farsighted?
Yes,
Okay. So
most people are nearsighted.
Right.
And so most people have the diverging. If you're farsighted, then you have a converging lens.
So how do contact lenses work?
Same way. We will talk all about this. In fact, I will have you measure your prescription for your eyeglasses in a very crude fashion. And if you don't have one, that's great. I wish I could say the same, but yeah, I have them. I just don't ever wear them. Okay. This stuff here is showing you what I showed on the screen or on the physical demonstration, except for its pictures instead of seeing it happen. The normals to the surface, is like that. So parallel ray, when it comes in, is going to bend toward the normal. When it goes out, the normal is like this, and it's going to bend away. This only shows one bend, right? It doesn't show two bends. Even though in reality there are two bends. And that's what we call the thin lens approximation. The thin lens approximation says that we just treat the bending on the front surface and the back surface as if it was at one place in the center of the lens. If a lens is thin, it makes our calculations simple. If it's a thick lens, and you have to admit, the lenses I use for the demonstration are thick, then the equations I'm doing don't perfectly explain it. The lenses you wear in your eyeglasses are close enough to thin that it's fine. But the ones I'm using are a little thick. So if it was thick, you would have actually had the light do something like this, having an intermediate ray like you saw in the demonstration. This is just going through the calculation, showing what's really happening, right? Showing you really have two curves, one at each surface. And then we get to, well, we've already talked about the focal length. The rays, look, same things, parallel ray, focal ray, vertex ray. Don't have a center ray possible if you're doing a thin lens ray drawing. But you have the same rules. So to construct the image for a lens, you once again will use exactly those three rays. You don't have any choices here. You have to use the parallel ray, the focal ray, and the vertex ray. And I did not do woo clap again today. So which ray, just blurt, which ray does not apply for a lens? Yeah, the center ray doesn't apply. So you can use any three of those four. If I give you a mirror, if I give you a lens, you have to use the three remaining. So here is a construction that is much more accurate than mine. So we have an object. Notice we're only using the tip of the object. Why don't we do the other side of the object? And that should be a little troubling, right? We don't use the other side of the object because if it's on the principal axis, it's going to make an image on the principal axis directly underneath the tip. And so we always put our objects so the tip is on the principal axis, and then we just, or one end's on the principal axis, and then we only find where the image is for the other side, and then just put a straight line to the principal axis for the rest of the object. So we only do 1 point. We could, I mean, if you were a glutton for punishment, you could make your object like this. But then you'd have to draw the rays. Parallel ray goes through the focal point. Oh, missed the focal point. Goes through the focal point. Vertex ray goes straight. And the focal ray goes through that. You see why doing things freehand for me is not really an option. They're close enough. And so I would have, that's the other side. They should be on top of each other. It's just doubling the work. Now there is something here that is different from what we did with the mirror. How many focal points does the mirror have? One focal point. But for the rays, we did the parallel ray that reflects through the focal point, and we did the focal ray that goes through the focal point and comes out parallel. For a lens, if it comes parallel, it's going to go through the focal point on the other side. If it goes through the focal point on one side, it's going to go out parallel on the other side. So you have to put the focal point on two sides, and the focal ray is going through the focal point on the near side if it's a converging lens, on the far side if it's a diverging lens. It's going through the focal point. The focal ray is going through the focal point, which is where rays that are parallel on the other side would meet. Not as good as it. Yes, that's the focal ray.
Why? I thought that focal ray would be like in the middle.
The focal ray goes through the focal point. So there's F. And comes out parallel. So this here is the focal ray. The parallel ray starts out parallel, and then it goes through the focal point where parallel rays will go. So this goes through the other focal point. So that's why you have to draw both focal points, and you have to keep in mind which one goes with parallel rays on the left side and which one goes with parallel rays on the right side. And then what remains is the vertex ray. At the vertex, you're going through parallel infinitely thin in the thin lens approximation, so it just goes straight. So this is for a converging lens. Here's what it looks like for a diverging lens. The parallel ray goes parallel, and then it comes out as if it came from the focal point where parallel rays on the left-hand side would have met. So with the demonstration, which I know she's taking a picture, so I'll wait. With the demonstration here, it needs to diverge as if it's from the point where the parallel rays met. So the parallel ray is coming as if it came from that focal point. Notice in this picture, the parallel ray went through the focal point on the right-hand side. Here it comes as if it's from the focal point on the left-hand side. So doing a diverging versus converging lens, you have to keep in mind where the actual focal point is. This is the actual focal point. This is the secondary focal point. Whereas here, this was the actual focal point, and this was the secondary focal point. The one that really confuses people is the focal ray for a diverging lens. Because the focal ray needs to go through the focal point that would make it come out parallel, which is the focal point, the secondary focal point. So the parallel ray is coming like this. It hits the lens here. It doesn't actually complete this part, which is why it's not shown in blue. That's what it would have done, but because of the lens, it comes out parallel.
Why is the principal and secondary focal point switch between diverging and converging?
Because for a diverging lens, parallel rays like this will all meet here. So that's the
where they all meet.
That's the principal focal point. Yes. For the diverging lens, parallel rays will all meet back here. Extrapolations. Right, so it would go, the actual ray is going to go like that. The actual ray is going to go like that. And if you extrapolate back, this is where they would meet. So that's the principal focal point for a diverging lens. That's why the principal focal point for the focal length for diverging lens is negative. So another way to keep this straight is if it's a negative focal length, then the principal one is on the left. If it's a positive focal length, the principal one is on the right. And the focal ray is always going to the secondary focal point. The parallel ray comes out as if it came from the principal focal point.